For centuries, we've had this dream, right? Giving sight to the blind. It's the kind of thing you'd expect to see in a sci-fi movie. But here's the thing. It's actually happening. It's becoming a reality. So today, we're going to dive into the absolutely fascinating world of the bionic eye.
And that really brings us to the big question, doesn't it? The one that's pushing researchers, engineers, and doctors all over the world. The answer they're coming up with, well, it's not a simple yes or no. It's complicated, but it's also incredibly hopeful.
Okay, so what is a bionic eye, really? The technical term is a visual prosthesis. Basically, it's an electronic device that gets surgically implanted to bring back some level of vision. And a key thing to get here, it's not about swapping out an old eyeball for a new one. Nope. It's all about creating a brand new pathway for visual information to get to the brain.
And you know what's crazy? This idea isn't new at all. We're talking about the 18th century. Ben Franklin and guys like him were already kicking around the idea of using electricity to create sight. Wild. But the real game changer, the thing that blew the doors open, was the cochlear implant, the bionic ear, back in the 80s. Its success was huge. It was proof. It showed us that yes, we can connect technology directly to the human nervous system. And that breakthrough really paved the way for everything we're seeing with the bionic eye today.
All right, let's get into the nuts and bolts. How in the world do you turn an electrical signal into something the brain can actually see? Well, the technology is just incredibly clever.
The best way to think about it is to go back to that cochlear implant, right? That device skips over the damaged parts of the ear and stimulates the auditory nerve directly. A bionic eye? It's the exact same principle, just for vision. It bypasses the damaged cells in the eye to stimulate the remaining healthy nerve cells in the retina or even the brain.
Now, it's important to know these devices aren't a fix for every kind of blindness. They're designed for a specific situation. The best candidates are people who've lost their sight because their photoreceptors have degenerated. You can think of photoreceptors as the tiny light-sensing pixels at the back of your eye. So in conditions like retinitis pigmentosa, those cells just fade away. But here's the crucial part. The optic nerve, that's the main cable running from the eye to the brain, it has to be intact. And ideally, it needs to have fully developed before the person lost their sight.
So how does this magic actually happen? How does a bionic eye take what's in front of you and turn it into a picture in your head? It's a really cool four-step process. Okay, step 1, a camera, usually mounted on a pair of glasses, captures the scene. Step 2, a little processor you wear converts that image into a simple electrical signal. Then, step 3, that signal gets beamed wirelessly to the implant inside, which then stimulates the nerve cells with a pattern of electrical pulses. And finally, step 4, and this is the amazing part, the brain learns to interpret those patterns as flashes of light, and it pieces them together to form a basic image. And look, this isn't just some science experiment in a lab. This stuff is out there, in the real world. So let's take a look at some of the amazing devices that have actually made this happen.
The big one, the first major breakthrough that actually hit the market, was a device called the Argus II. It was developed by a company called Second Sight, and when it got approved, man, that was a huge moment. It was the point where commercial bionic eyes stopped being a futuristic fantasy and became real.
But what's really incredible is how long it took to get there. This was not an overnight success. We're talking more than 20 years of work, from the very first concept back in the early 90s, through a 16-electrode prototype, all the way to the 60-electrode Argus II that finally got that FDA approval. It was just a true marathon of scientific grit and effort.
But stimulating nerves isn't the only game in town. There's another approach that's completely different, the implantable miniature telescope. And yeah, it's pretty much exactly what it sounds like, a tiny telescope that's actually placed inside the eye. It doesn't create an image with electricity. Instead, it just magnifies whatever the person is looking at by about 3 times, and it projects that bigger picture onto the healthy parts of the retina. The catch? Well, it's a big surgery with a large incision, and it's a no-go for anyone who's already had cataract surgery. And the potential here, it's just astounding. Listen to this quote from a German project for a device called the Alpha IMS. With its 1,500 electrodes, it allowed some patients to go from complete blindness to actually being able to read letters and identify things on a table. Just imagine that. Those are truly life-changing results.
But here's where the story takes a turn. This is the tough, cold reality of working on the cutting edge. Despite those amazing successes we just talked about, the company behind that Alpha IMS implant, they had to shut down. It's a stark reminder of the huge challenges innovators are up against. from navigating these super rigid regulatory systems to the simple fact that sometimes the results just aren't consistent enough from one patient to the next. And if you want to understand the real human impact of this technology, you just have to look at someone like Diane Ashworth. She was one of the very first people to get an Australian-developed bionic eye, and the experience was so profound for her that she actually wrote a book about it. Her story really puts a face to all this complex science and reminds us what this is all about.
And that's the thing, there's not just one path to restoring sight. So the most common way is stimulating the retina, like we've been talking about. But some researchers are trying to bypass the eye entirely and go straight to the brain's visual cortex. That's called an intracortical prosthesis. And then you've got this other wild idea, photovoltaic implants. These are basically tiny solar panels inside the eye, powered by light that's projected from a special pair of goggles. It's just an explosion of creativity in this field.
So, with all this incredible work happening, where is it all going? What does the future of bionic vision actually look like?
If you had to sum it up in one word, it would be resolution. Think about it. The Argus II had 60 electrodes. The next generation of devices, they're aiming for over 1,000. With 1,024 electrodes, scientists believe they might be able to provide vision that's clear enough for someone to recognize a face or read large print. The level of detail, the quality of this artificial sight is just getting better and better.
Okay, but we have to be realistic here. It's really important to manage expectations. The key phrase to remember is functional vision. We are talking about restoring the ability to see light and dark, to make out large shapes, maybe even read a few letters, and that in itself is a monumental achievement. But it's not the same as getting back the perfect, rich, detailed sight that a healthy eye provides, at least not yet.
And that really leaves us with the big final question, doesn't it? I mean, the journey from Ben Franklin just thinking about this stuff to today's actual camera-powered implants is absolutely incredible. But will this tech ever truly replicate the complexity of our own eyes? The millions of pixels, the vibrant colors, the sheer richness of human sight? That's the challenge for the next generation of pioneers to solve.